right. Good afternoon, everyone. Are there any questions? All right. So let's finish up with our last example, last two examples. Okay, so in this example, it says we want to find the circulation and flux on the field F around and across the closed semicircular path that consists of the semicircle arc, or R sub 1. And bring this a little closer to myself. See, R sub 1 of t is defined as a cosine of t in the ith direction plus a sine of t in the j direction, where t is bounded between 0 and pi. And then we've got the line segment, which we're going to call R sub 2. It's defined as t in the ith direction, where t is bounded between negative a and a. And our field is x squared in the ith direction plus y squared in the j direction. Okay, so what we're going to do is to deal with each of the pieces separately. Okay, so we're going to deal with the first piece along this in respect to the force. Okay, so we're going to say that our force 1 function is going to be defined, and basically we're going to take this and plug it in for x, this and plug it in for y in the force function, so we get everything in terms of time. So we're going to have a squared cosine squared of t in the ith direction plus a squared sine squared t in the j. Okay. All right. So now the next thing we're going to do is we're going to take the derivative in respect to r sub 1 in respect to t. So if we do that, we're going to get negative a sine of t in the ith direction plus a times the cosine of t in the j direction. Okay, so to do this first circulation, we're going to look at the integral from a to b of f sub 1 dotted with d sub 1 d r sub 1 t dt. So we're going to look at the dot product of those two vectors. Any questions so far? Okay, so this is what it's going to look like. So for the first circulation, going to be the integral, and our first set of limits of integration are going to be based on this, because this is the path that we're following. So we're going to integrate from 0 to pi. Okay. Of. And then what we're going to do now is the dot product of these two. Okay. So if we do that, we're going to end up with negative a cubed. Go back. Cosine squared t sine of t. And then for the second piece, it's going to end up being plus. And we're going to have a cubed sine squared t cosine t, and then dt. So basically what we need to do is to simplify this. So if we take a look at this, we realize that we can factor out a cube sine t cosine t. And then what we're going to be left with is negative cosine t hold on. I'm making this way too hard. Sorry about that. Don't need to do all that. We're just going to dive in and integrate. So we can integrate each of these pieces separately, okay, since it's addition. Okay, so for the first piece, we're going to say, okay, it's going to be a u sub, so we're going to let u be the cosine of t. So du would be negative sine t dt. Okay, now we've got a negative sign here in the sine of t. So basically we've got everything as far as what we need for the u sub. And keep in mind that a cubed is a constant. So we're going to have, basically we're integrating u squared. So we're going to get 1/3 a cubed cosine cubed t. Okay. Now for the second piece, it is going to be a u sub again. And what's u going to be for this? Yes. So it's going to be the sine of t. So du would be cosine t dt. And we've got the cosine t dt, so we're ready to go. So again, a cubed is a constant, so we're going to end up with plus antiderivative u squared is going to be 1/3. We're going to have a cubed, and we're going to do sine cubed t, and then we're going to evaluate this from 0 to pi. Now, if we plug in pi, for this piece, we're going to end up with negative 1/3 a cubed. For this piece, we're going to end up with 0. And then we're going to do minus. At 0, the first piece we're going to end up with going to be 1/3 a cubed. The second piece is going to be 0. So we're going to end up with negative 2 a cubed over 3. So this will be the circulation along the first path for that field. Any questions? Okay, so the next thing we're going to do is to find the flux. So the flux for this curve, we're going to call it flux 1. Okay, this is going to be equal to, it's going to be the line integral, and then we're going to have m1 dy minus n1 dx. Okay, so what we need to do is to go through and identify what m1 is, n1 dy and dx. Okay, so let me go back to our original function f1. Okay, and the way we defined it, which was a squared cosine squared t in the I direction plus a squared sine squared t in the j direction. Okay, so in this format, this represents m1, this represents n1. Okay, then for the next piece of this, we need to identify what dy and dx are. Okay, so here's what we're going to do. So we look at dr1, taking the derivative of r1 in respect to t, and we said that was negative a sine t in I direction plus a cosine of t in the j direction. Okay, so the first part of this would represent dx, the second part of this would represent dy. Any questions there? Okay, so now let's fill in what the flux would look like. So the integral that we're going to deal with for the flux, okay, now the limits of integration are given to us because it's the bounds um, for R1, all right, and that's going to be from 0 to pi, okay, so if we plug in based on the formula, so we're going to take m1, which is ax squared, a squared, excuse me, cosine squared t, and we're going to multiply that by dy, which is going to be a cosine of t. Then we're going to do minus, then we're going to take n1, so that's going to be a squared sine squared t, and we're going to multiply it by dx, which is um, negative a sine of t. Okay, and again, don't forget the dt. dt goes for both pieces. Okay, any questions? All right, so now the fun part is just getting this integrated. So we're going to have this integral from 0 to 1. Now, when I look at this, okay, I realize that I can factor out what?
AQ.
Yeah, a cube is the only thing that I can factor out because I can't really touch with the sines and cosine because they're not shared by both. So I can deal with the a cubed. So a cubed, which is a constant. So what I'm left with is cosine cube t. Now, it's going to end up being plus because of the negative and a negative here. And then we're going to have sine cube t dt. Any questions there? So now what we're going to do is just kind of do a little break apart on each of those and be able to transform. So keep in mind that for the cosine cubed, we can write it as cosine squared t, cosine of t, and then for the sine cubed, sine squared t, sine of t. Okay, and then I'm going to use Pythagorean identities to rewrite the squares. So I'm going to have a cubed integral from 0 to pi. This is going to be written as 1 minus sine squared t times the cosine of, not cotangent, but cosine of t. And then plus for the second piece, we're going to have 1 minus cosine squared t times sine of t. And again, dt. So we're going to end up with a cubed. All right. So essentially what we're going to do is to multiply this out, okay, and then integrate. So if we multiply cosine t times 1, we're going to get cosine t. But what's the antiderivative of cosine t?
Sine t.
Okay, so we're going to have sine of t. All right, and then for the second piece, we're going to have sine squared t cosine t, and that's going to be a u sub. So we're going to end up getting negative 1/3 sine cube t. Okay. All right, so now let's look at the next part. So if we multiply through by sine of t, okay, so sine of t times 1 is going to be sine of t. Antiderivative of that is going to be negative cosine of t. And then for the next part, it's going to end up being plus 1/3 cosine cube t. And then we're going to evaluate this from 0 to pi. So what we're going to have when we evaluate at pi, this is going to be 0, this is 0, this is going to give us 1. This is going to give us negative 1/3. So we're going to have 1 minus 1/3 minus, then when we plug in 0, 0, 0, negative 1, 1/3. So negative 1 plus 1/3. So we're going to have a cubed times, basically we're going to have 2 minus 2/3, which is going to give us 4/3. So we're going to end up with 4/3 a cubed. Any questions?
So we did not attach the R2, right?
Say again.
Sorry, we did not attach the R2, right? From the question, R2T.
No, we haven't done the second part yet.
Oh, okay.
Okay. So all we've done so far is define the circulation and flux for R1. We
Oh, I
haven't
see.
dealt with R2 yet.
All right.
Okay. R2 is going to go a little bit faster. Okay, so now I'm going to deal with the second one. All right, so for the second one, we know that f was defined as x squared in the I direction plus y squared in the j. R2 was defined as t in the I direction, and where t was bounded between negative a and a. So first thing we're going to do is to find the force field in terms of t based on the second path. So we're going to basically plug t in for x. Now in place of y, we're basically going to put in 0 because we don't have a j component in that path. So all we're going to end up with is t squared in the I direction. All right, so next, if we look for dr sub 2 dt, so what would the derivative of the second path be?
1 in the I direction.
Right. Okay. So when we are doing the circulation for the second path, all right, so this time we're going to integrate from negative a to a. And then if we do the dot product of f of 2 and dr sub 2 of t, we're just going to end up with t squared dt. Well, if we integrate this, it's going to be 1/3 t cubed, evaluated from a to negative a. So we're going to end up with 1/3 a cubed. Now it's going to be minus, but let's keep in mind when we take negative a and cube it, it's going to give us what?
Minus.
It's going to be minus, but we got two minuses, makes it a plus. So we're going to end up with 1/3 a cubed. So we're going to end up with 2/3 a cubed for our answer. Okay, so for the flux, all right, so for the flux, the second, it is going to be the line integral, and we're going to look at m2 dy minus n2 dx. Okay, so let's identify each piece. What's m2 going to be?
T squared.
Right. Now, n2 is going to be what?
0.
Good. All right, then next, we have dy, which is going to be what?
0.
Good. And then dx is going to be what?
1.
Or, yeah, 1 or just dt. Okay. Now, let's keep in mind that if we fill this in and kind of write it underneath, so we're going to have here t squared times 0 minus 0 times dt. Well, what is that going to give me?
Zero.
It's going to give me 0. So that's the flux for the second piece. As I said, the second piece is a lot easier because the function is a lot easier, a lot more simplistic. Okay. All right. So now let's finish up the problem. Okay. So what we want to do is we want to find the total circulation. So it's going to be the circulation from path 1 plus the circulation per path 2. So what was the circulation for path 1?
Negative 203 a cubed.
And then what was the circulation for path 2?
2 over 3 a cubed.
So we get a circulation of what?
0.
0. Okay. Then next, let's find the flux. So we're going to do the flux for over the first path plus the flux over the second path. Now, what did we say the flux was over the first path?
4 over 3 a cubed.
And what did we say it was for the second path?
Is that 2 over 3 a cubed?
Mm-mm. So what did we find the flux to be? Yeah, it was 0. So we end up with 4/3 a cubed, and that would be the flux. Okay, so the circulation is basically telling us how the flow is moving, and since the circulations of the two paths cancel, that means we have no circulation along for this field over these two paths. But we do have a flux over this field over the two paths.
Can you go back to a slide? Oh, I see. I see how we got 0. All right, thank you.
Okay, you're welcome. Okay, any questions? Now, that was kind of long, and that was just because of the fact that we had two paths to deal with. If you just had one path, then this problem's not really that bad. Okay, all right, and let's look at our last example. So in this last example, it says F is the velocity field of a fluid flowing through a region in space. It says find the flow along the given curve in the direction of increasing t. Okay, so in order for us to find the flow, so this is going to be the integral from A to B of, we're going to have our force, we're going to have our force field. We're going to dot it with the derivative in respect to t of our curve, dt. Okay, so the force that they give us is t squared in the I direction plus yz in the j direction plus y squared in the k direction. Now, the curve is defined as 3t in the j plus 4t in the k. So, first thing I have to do is I have to transform the vector field in terms of time. So, what would I put in for x? I'm going to put in 0. So I'm going to have 0 squared in the I direction plus, in place of y, what am I going to put in?
Three t.
Right. And in place of z, what am I going to put in?
4t.
Okay.
4t.
And that's in the j direction plus, and we've already identified that y was 3t, and we're going to square that, and that's in the k direction. So our vector field for this in terms of time is going to be defined as 12t squared in the j direction plus 9t squared in the k direction. So here's our velocity field. Now, the other piece of it that we need, based on the formula, we need to find dr dt. So what would dr dt be equal to?
Three in the j direction.
Okay.
Plus 4 in the k direction.
Correct. Okay. So we found our dr dt. So now what we're going to do is the dot product of these two. Now, in the problem, they tell us how t is running. T is running from what to what?
0 to 1.
Okay. So we're going to have that the flow is equal to the integral. We're going to go from 0 to 1. All right. So if we multiply the I components together, what are we going to get?
Zero.
Oh yeah, I components is 0. Sorry, I meant the j components. If we multiply the j components together, what are we going to get?
36 t squared.
Okay, so we're going to have 36t squared plus. Now, if we multiply the k components together, we're going to get what?
32 t squared.
Not 32.
Sorry, 36.
Yes. So we're going to get 36t squared. Okay, dt. So really, we're looking at the integral from 0 to 1 of 72t squared dt. So if we integrate this, what do we end up with?
Uh, 24 t cubed.
Okay, so 24t cubed, evaluate from 0 to 1. So our answer is going to be what?
24.
Yes. And that would represent the flow. Okay. Any
So,
questions?
So the flow and the circulation formula are the same, right?
Um, keep in mind that the circulation, what's the difference between circulation and flow? Circulation is on a, circulation is on the open path. Flow, excuse me, I'm saying that wrong. Flow is on an open path, whereas circulation is on a closed path. So the difference between flow and circulation, they're done the same way, but just keep in mind, it becomes circulation when it's a closed path.
I see. All right. Thank you.
Okay? Any other questions? Okay. All right. So, okay, so let's hold for 1 second. I need to move back to my office area. right, sorry about that. I was having internet issues before your class started, so I had to move to a different location to use my data until the internet came back up. So, okay. So, are there any questions on dealing with the section over um, vector fields, work, circulation, and flux? Okay, so the next section we're going to take a look at is going to be dealing with path independence, potential functions, and conservative fields. Okay, and let me pull that up real quick. Because there's a lot of formulas in here, and I don't want to read them out and not be able to point them out. So, oops. Let's see here. Okay. So, if we take a look at this, okay, and this is dealing with the independent paths, potential fields, and conservative fields. Starting off first with the definition, it says the field F, let field F be a field defined on an open region D in space, and suppose for any 2 points A and B in D, the work integral from A to B of F dot dr done for moving from A to B in D is the same for all paths from A to B. Then we say the integral F dot D is independent of D, and the field has a conservative D on D. Now, the reason why this is important is that if it's a conservative field, then we're able to do some extra things to it. So we'll be able to integrate it and things like that. If it's not conservative, then it creates issues. Okay. Next definition. It says if F is a field defined on D and the capital F is equal to the gradient of F for some scalar function F on D, then F is called a potential function for F. And we're going to talk about what potential functions are and how to find those. Okay. Fundamental theorem of line integrals. All right, so this is just basically just telling us how to evaluate a line integral when we are in 3D. Okay, so instead of us converting it over in terms of time, we'll be allowed to leave it in terms of x, y, and z to be able to integrate. Okay, so this is what this theorem is allowing us to do. All right, next, conservative field are gradient fields. It says let f equal m in the I direction plus n in the j direction plus p in the k direction be a vector field whose components are continuous throughout an open connected range D in space. The f is conservative if and only if f is a gradient field gradient of f for the differential function of f. And we're going to talk about how we determine if a conservative field is if a field is conservative. We're going to talk about how to do that. Okay. Closed loop properties of a conservative field. So if you take the integral of the field of f dotted with r, it should be equal to 0. So that means it's closed for every loop in D. And the field has to be conservative. So with that in mind, if we kind of think about the example where we're doing the circulation, okay, along those two paths, essentially in a way, except for we haven't verified the second component, but it kind of satisfies that first component in that it's a closed loop because our when we looked at the circulation, it was equal to 0. All right, next piece is component test for conservative fields. So this is basically what the test looks like, and instead of trying to read this off and make sense of it, when we do the examples, I'll show you what this is. Now, it's not as easy as just checking one. You have to check all possibilities when there's 3 variables. Okay, so if there's only 2 variables, there's only 2 possibilities you have to check. But since we have 3, if it's 3 variables, you do have to check every possibility. And again, when we go through the examples, I'll show you how this is going to work. All right, and then next, a couple of definitions. You can express m of xyz dx plus n of xyz dy plus p of xyz dz as a differential form. A differential form is exact on the domain in space if you have this and it's equal to the partial respect of f in respect to x dx, partial in respect to y dy, partial f in respect to z dz. This is df, okay, where there's the scalars. And again, I'm going to show you how this is going to work in order to be able to do this. And then the last thing we have is the test for exactness. So the test for exactness is kind of falls in line with the test for conservative. So if it's conservative, it's exact. All right. So now let's take a look at our examples. Okay. So let me switch. Okay. So the first example we have is this. So we have the field defined as f is equal to y sine of z in the I direction plus x sine of z in the j plus xy cosine of z in the k. Okay, and what we want to do is to test to see if it's going to be a conservative field. Okay, so what we're going to look at first is we're going to look at the partial of p in respect to y and compare it to the partial of n in respect to z. So what we're going to do first is identify what m, n, and p, m, n, and p are. So this is going to represent m, this is going to represent n, this represents p. Okay, so if I take a look at this, if I take the partial of p in respect to y, that means I'm taking the partial of this in respect to y. So if I do that, I'm going to end up with x cosine of z. Okay, now let's take a look at n, and let's take the partial in respect to z. So here's n. What is the partial of n in respect to z going to be equal to? Yes, it's going to be equal to x cosine of z. So that leg is satisfied. Those two partials are equal. So next, we're going to move down and take a look at the next set. We're going to look at the partial in respect of m in respect to z. and see if it's the same as the partial of p in respect to x. Okay, so here's m. So what is the partial of m in respect to z? Yes, so it's going to be y cosine of z. Okay, now we're going to take the partial of p in respect to x. So what's the partial of p in respect to x?
The same thing.
It's the same thing, so they are equal. Okay. All right, so the final check that we have to do, we have to check that the partial of n in respect to x and compare it to the partial of m in respect to y. So what's the partial of n in respect to x?
Sine z.
Right. Now we're going to look at the partial of m in respect to y, and that's equal to what?
Sine z 2.
Sine z again. So since all these partials are equal based on this first set of partials are equal, this set of partials are equal, this set of partials are equal. Since that is true, we say that this field is conservative. So we say the field is conservative. Any questions? Okay, so next, let's look at another example. So next example we have is this. Okay, so we have the f is equal to e to the z cosine of y in the I direction minus e to the z sine of y in the j direction plus z in the k direction. So the first time around, we're looking at to show that the partial of p in respect to y is equal to the partial of n in respect to z. Okay? And again, we can say this is m, this is n, this is p. So what is the partial of p in respect to y? It's 0. And then what is the partial of n in respect to z? It's 0. So we know that both sets of those partials are equal to 0. Good. So that one checks off. So next we're going to look at the partial of m in respect to z and compare it to the partial of p in respect to x. So if I take a look, what is the partial of m in respect to z? Is 0. Good. Now, what's the partial of p in respect to x? It's 0 also. So we've shown that they are equal. Okay. Then the last thing that we have to look is the partial of n in respect to x. Show that that's equal to the partial of m in respect to y. Okay, so if I take the partial of n in respect to x, what will I get?
E to the power x sine y.
Close.
Does the negative have to do something with that?
Yes, it
Yeah,
does.
okay.
So it should be negative e to the x sine of y. Okay, so you got to keep in mind, you just can't throw that away. Okay, so next, let's look at the partial of m in respect to y. So if I do that, what do I get?
We get the same answer.
Yeah, you get the same thing. Okay, so basically every piece of this checks out. So this makes it a conservative field. Okay, so it is going to be a conservative field. Any questions? Okay, so next, in next set of examples, we're going to find, it says find a potential function f for the field f. Okay, so our first example is this. We have that f is equal to y plus z in the I direction plus x plus z in the j direction plus y plus n in the k direction. Okay, so here's what's happening with this problem. We are basically given the derivative. And what we're going to do, the potential function is the original function. Okay, so that is what we're looking for. All right, so this is how it's going to work. Okay, so what we're going to do is to deal with just each, we're going to look at the partials of each piece. Okay, so we're going to look at the partial of f with respect to x, the partial of f in respect to y, and the partial of f in respect to z. Okay, so the partial of f in respect to x is going to be this first component. So this is going to be y plus z. So now what we're going to do, that arrow, what it's going to do is tell us to integrate. So we're going to integrate this in respect to x. So if we integrate this in respect to x, we're going to end up with this. We're going to have x times y plus z, okay, plus. Now, with this, we're going to have some new function that's going to be created, okay? And we're going to say the function is going to be a function in terms of I gotta look at my thing real quick. So it'll be a function in terms of g and z. Okay. So next, what we're going to have and I need to do a better job of explaining this because it's kind of confusing. One whole second. I thought I was wrong. Okay. Let me back up just a step. I thought I was wrong in my notes, and I am. Okay. So I'm going to create some function g in terms of y and z. So what's happening is that since I'm integrating with respect to x, I'm going to have x times this. Then it's going to create a function based on the other two variables that I'm not integrating in respect of. So we're going to call it a function g that's being defined in terms of y and z. Okay? Does everyone understand that so far? Okay, so next, what I'm going to do is I'm going to take the derivative. I'm going to take the, I'm going to look at the partial of f in respect to y. All right, so if I look at the partial of f in respect to y, this is going to be equal to x plus the partial of g in respect to y. Okay, now here's how I got this. Okay, this right here essentially is my function fyz. Okay, so if I take the partial of f in respect to y, so if I take the derivative of this in respect to y, all I'm going to have left is just x. If I take the partial of this in respect to y, we don't necessarily know what it is, so all we can do is write it as partial of g in respect to y. Okay, now this is equal to the second component of the uh, of the field f. So this is going to be equal to x plus z. Well, if I solve this, the x's will cancel. So I'm getting that the partial of g in respect to y is equal to z. Now, if I integrate this, I'm integrating respect to y, that's going to give me that and let me remove this little bit so that I have more room. So that's going to give me, and let me just take this, oops, and bring it down. So we're going to have the partial of g in respect to y is equal to z. So if I integrate this, that means that this now becomes g of yz, and that's equal to, if I take the antiderivative of this in respect to y, it's going to be zy. Now, I'm going to have some new function created, h, which is going to be defined in terms of z. Okay? So, before I move on, let me go back and explain everything again. Okay, so the way this works is we start with the first component. Okay, and we said that the partial of f in respect to x is equal to that first component. Now, when we integrate this, it's going to create a function fy and z. If I integrate this in respect to x, it becomes x times y plus z. Then I'm going to have plus some new function that is defined in terms of the two variables that I didn't integrate with. And that's y and z. Okay. So now I've created this function f. All right. So now what I want to do is take the partial in respect to y. So if I take the partial of this in respect to y, that gives me x. If I take the partial of this function g in respect to y, we just write it as the partial of g in respect to y. Okay? Now, this whole expression is equal to what f, the partial of f in respect to y is. Well, that's going to be the next component. Okay? So that's why we said this is equal to x plus z. Well, the x's are going to cancel. So what I end up with is that the partial of g in respect to y is equal to z. Now, if I integrate this, okay, so if I integrate this side, it's saying that g of yz is going to be equal to, if I integrate this in respect to y, that gives me x zy. Then I'm going to have plus some function that is only defined in terms of the only variable that I haven't used yet to integrate by, which is z. And that's how I got the h of z. Any questions so far? Okay, so now I'm going to write out what my function is. My function f of x, y, z is equal to, okay, it's going to be x times y plus z, and then it's plus g of y, z. But we found what g of y, z was equal to. So what we're going to have is x times y plus z plus, we said that g of yz is equal to yz plus some new function defined in terms of x. Any questions? So now what I'm going to do is I'm going to take the partial of f in respect to z. So if I do that, what's the partial of this first component in respect to z? It's just x. Plus, what's the partial of the second in respect to z? It's just y. Plus, now, if I take the derivative of the, keep in mind, we use partials when there's more than one variable. Since it's down to a single variable, it's just going to be now a derivative. Okay, so we're going to end up with x plus y plus h prime of z. Now, this is going to be equal to that last component of f. Okay, and the last component of f is x plus y. Well, if we solve this, x's cancel, y's cancel. So all we have left is h prime of z is equal to 0. So if we integrate, we're going to have that h of z is going to be equal to some constant. And we know that the antiderivative of 0 is 0. But you always have to remember, since it's an indefinite integral, you're going to have a constant of integration, which is the c. Any questions? Yep. Okay. So that means that our potential function is going to be defined as follows. It's going to be f of x, y, z is equal to, excuse me, x times y plus z plus y z plus, now in place of h of z, excuse me, we're going to put c. And this represents our potential function. Questions? Okay, so let's try another one. All right, so in this example, okay, so this time we're told that f is equal to y times the sine of z in the I direction plus x sine of z in the j direction plus xy cosine of z in the k direction. Okay, so how we're going to start off is that we're going to say that the partial of f in respect to z. Now, this is going to be equal to the first component. All right, so the first component is defined as y times the sine of z. All right, so now we're going to integrate. Now we're going to integrate in respect to z. I mean, excuse me, in respect to x. So that means that this now is going to turn into a function of x, y, and z, and this is going to be equal to. Now, if I integrate this in respect to x, what will it become?
X1 sine z.
Okay, so we're going to have xy sine of z, and then we're going to add on a function g that is defined in terms of what?
Point z.
Y and z. Okay. Any questions there? So now what we're going to do is we're going to take the partial of f in respect to y. Now, we're taking the partial of this right here that I'm underlining. Okay, so if I take the partial of f in respect to y, what will I get for this piece? Yes, I'm going to get x times the sine of z plus. Now, if I take the partial of this in respect to y, all I can do is write it as the partial of g in respect to y. Now, this is going to be equal to what?
X sine z.
Right? Which tells us this, that the partial of g in respect to y is going to be equal to what?
0.
Okay. Now, if we integrate this in respect to y, the left-hand side is going to become a function in terms of y and z, and that's going to be equal to, well, the antiderivative of 0 is going to be what?
0.
0. But we're now going to add on a function that is in terms of what?
C.
Yes. So we're going to have a function h in terms of z.
Oh, yeah.
Okay. Any questions there?
I have a question. So
Yes.
from the x sine z, like where I'm like confused. So so I know that that tells us something, but then like where did you get the partial of g with respect to the partial respect of y when it equals 0? Like I'm confused
Okay,
on that.
so keep in mind that I'm taking the partial of f in respect to y, right?
Mm-hmm.
Okay, so when I take the partial, and I'm just doing the partial for each of these pieces in respect to y,
Mm-hmm.
oops, sorry, hold on one second. There you go, it's a y. Okay, so remember that if I take the partial of f in respect to y, for the first component, I'm going to get x sine of z. For the second component, remember, I don't know what that function is. So what I'm doing is that I'm just going to take the partial of that function in respect to y. Does that make sense to you?
Yes, that part makes sense. But then the third line where it's like the
So
partial
where
of
I got
g, yeah, to get 0, I was like, what?
okay, so once I finish that partial, I know that that partial is equal to the next component of capital F. That's equal to, that's why I put xz here. Well, if I look, ignore this. So I have that, I'm solving this equation right here. So I can subtract xz from both sides. So that's why I get that the partial of g in respect to y is equal to 0. Are you okay to there?
Yes, I understood it now.
Okay.
Sorry about that. Thank you.
No problem. No problem. Okay. Any questions? That's basically it. Okay. So basically what you're doing is that it follows a certain order. So basically you start off with the first component, create the function, then you're going to take the partial of the function. Once you do that, that's going to be equal to the second component. Then you're going to solve for G and find out what that's going to be. And that's going to produce H. Then you got to find out what H is to finish it out. Okay, so now what I'm going to do, since I know what G of YZ is equal to, I'm going to replace it in the function. So I'm going to have, there we go, f of x, y, z. And we said that was equal to xy sine of z plus g of yz. We established that g of yz is equal to h of z. So the last thing I need to do is I'm going to do the partial of f in respect to z. So if I do the partial of f in respect to z, the partial of this in respect to z is going to be xy cosine of z, plus if I do the partial of this in respect to z, since it's only one variable, it's a derivative. And this is going to be equal to the last component of the capital F, okay, which is equal to xy cosine of z. So what that tells me is that h prime of z is equal to what? Is equal to 0. So now when I integrate, that tells me that h of z is going to be equal to what? C. Okay. So our potential function, okay, is going to be xy sine of z plus c. Okay. Any questions? So to get your head wrapped around this, okay, essentially what we're doing is that f is the gradient and you have your different components. What we're trying to do is to find the function that we're finding the gradient of. And this is the function that we were finding the gradient of. Okay, so when we were doing the gradient, we were saying, okay, here's our function. And when we were done with it, this was the gradient. So now what we're saying is, okay, here's the gradient. What was the original function? Any questions? Okay. All right, so let's take a look at another example. All right, so our next example, it says show that the differential form in the integral is exact, then evaluate the integral. Okay, so in this example, we're looking at the integral from one, not what I'm writing. So it's integral from 1 1, 2, 2, 3, 5, 0 of yz dx plus xz dy plus xy dz. Okay, so if we want to show that it's exact, so again, keep in mind that showing it's exact is it's basically the same method of showing that it's conservative. It's conservative. So what we're going to do first is to take a look at the partial of p in respect to y and show that that's equal to the partial of n in respect to z. Okay, so this would be your m, this is n, this is p. Okay, so if I look at this, what's the partial of p in respect to y? So what's the partial of p in respect to y? Yes, it is going to be x. So now let's look at the partial of n in respect to z. That's going to be what? X also. So we know that both pieces are equal to x. Okay, so that checks out. So next, I want to look at the partial of m in respect to z and show that's equal to the partial of p in respect to x. Okay, so what's the partial of m in respect to z? It is 1. And what's the partial of p in respect to x? It's y also. So that checks out. So the last thing we're going to do is to check the partial of n in respect to x and show that that's equal to the partial of m in respect to y. Okay, so if I take the partial of n in respect to x, what will I get? I get z. And then what's the partial of m in respect to y? It's z also. So I know that this is an exact equation. Okay, so now what I need to do, okay, is solve this. So I know this is an exact. All right, now since it's an exact, then the method that I just did to come up with the potential function is the method that I'm going to go through. Okay, so here's what I'm going to have. All right, so I'm going to start off with the partial of f in respect to x. That's going to be equal to the first component. All right, so the first component was defined as what?
yz.
Yz. So this is going to be equal to yz. So when I integrate, the left-hand side becomes the function f of x, y, z. And this is going to be equal to, so when I integrate the right-hand side, I'm going to end up with what? So when I integrate the right-hand side, I'm going to end up with what?
Hyz
X, Y, z
plus g of yz.
plus some function in g that's in terms of y and z. Okay. Everyone okay with that? So my next step is I'm going to take the partial of f in respect to y. So what would the partial of f in respect to y be?
xz
Okay, so we're going to have xz plus,
partial of g over partial of y with
okay,
respect to
partial
y.
g in respect to y. Now, we know that this is going to be equal to what?
AC
Xz. So, we're going to end up with what?
0, like partial of g over y was 0
Equals
with
0,
zero.
right? So, we can say that, and I'm going to put an arrow here so we make sure everyone's following. So if we integrate in respect to y, that means we're going to have g of yz is going to be equal to what?
AC
Yes, we're going to have it equal to h of z. So now we can define our function f of x, y, z is going to be equal to x, y, z plus, in place of g of yz, we're going to put in h of z. So the last bit that we need is the partial of f in respect to z. So what is the partial of f in respect to z?
hy plus the derivative of h with
Okay.
respect to z.
Right. Now, we know that this is going to be equal to what?
Hy
It's going to be equal to xy. Therefore, we can say that h prime of z is equal to what?
0
So we can say that h of z is equal to what?
c
C. So our potential function f of x, y, z is going to be x, y, z plus c. Any questions?
So the integral is exact when the field is conservative, right?
Say again.
The integral is exact when the field is conservative, right?
Right. So since it's an exact, this is a conservative field, okay, and we need this because if it wasn't exact, then we wouldn't be able to solve it this way.
All right, I see. Thank you.
Mm-hmm. Okay. So now, basically, what we're going to do, since what we want to do is evaluate this integral, we're going to ignore the plus c. So we're looking at the integral from 1, 1, 2 to 3, 5, 0 of yz dz. I mean, excuse me, not dz, dx. Plus xz dy plus xy dz. So it's going to be equal to, well, we found our function. So what we're going to do is we're going to evaluate the function at the upper integral, upper limit, minus the value of the function at the lower limit. So if we put 350 into the function, what value do we get?
0
Minus. If we put the value 123 into, I mean 112 into the function, what value do we get?
0. I mean, sorry, 2.
2. So our value of the integral is -2. Any questions? Okay. All right. So let's go through one more example, and this will be the last example for today. And then we'll move into, we'll complete the other ones next week. Okay. So the next example, all right. So we're looking at this. We're integrating from 0, 0, 0 to 3, 3, 1 of 2x dx minus y squared dy minus 4 over 1 plus z squared dz. All right, so real fast, I'm just going to go through to show that it's exact. So if we do the partial of p in respect to y, so again, remember this is m, this is n, this is p. Okay, and we're trying to show that that's equal to the partial of n in respect to z. So the partial of p in respect to y is going to be 0. Partial of n in respect to z is going to be 0 also. All right, next, we're going to look at the partial of m in respect to z, showing that it's equal to the partial of p in respect to x. So if I look at m, the partial in respect to z is 0. If I look at p, the partial in respect to x is also 0. And then the final thing, we're going to look at the partial of n in respect to x and show that's equal to the partial of m in respect to y. So if I look at n and take the partial of that in respect to hold on, make sure I didn't goof up something. So in respect to okay. And if I look at that, partial of n in respect to x is 0, partial of m in respect to y is also 0. So we get them, they're all 0. Okay? Hopefully I didn't copy that problem wrong. Okay. All right, any questions? Yeah, if one of the pieces fail that is exact, then you can't solve it the way we've been solving it. Okay, so it has to, if it's not exact, then you have to solve it a totally different way. And if you take differential equations, you'll talk about how to solve it different ways if it's not an exact differential equation. Okay, so we've established that it is exact. So now what we're going to do is to find the potential function. So we're going to have the partial of f in respect to x. This is going to be equal to 2x. So if we integrate, we're going to have f of x, y, z. This is going to be equal to x squared plus some new function that's defined in terms of y and z. right? So now we're going to take the partial of f in respect to y. Well, if we do that, we're going to end up with the partial of g in respect to y. And this is going to be equal to the next component, okay, which is negative y squared. Well, if I integrate this, it's going to become that g of yz is equal to negative 1/3 y cubed plus some function in terms of z. Any questions so far? So what we have is that our function f of x, y, z is going to be defined as x squared minus 1/3 y cubed plus h of z. So now I'm going to take the partial of f in respect to z. So if I do that, I'm going to get h prime of z. And this is going to be equal to negative 4 over 1 plus z squared. So what that tells me is that this, when I integrate it, is going to be that h of z is going to be equal to negative 4 tangent inverse of t plus c. So that tells me that my potential function is going to be x squared minus 1/3 y cubed minus 4 tangent inverse of not t, but z, excuse me, plus c. Any questions? Now, since I'm looking to evaluate the integral, I ignore the plus c. Okay, so what I'm going to be looking at is this. I'm going to be looking at f of the upper limit, which was 3, 3, 1, minus f of the lower limit, which was 0, 0, 0. Okay. So if I deal with the first one, if I put in 3, 3, 1, okay, so if I put 3 here, it's going to be 9. 3 here, it's going to be 9. 1 here, I'm going to get pi over 4. So it's going to look like this. So it's going to be 9 minus 9 minus 4 times pi over 4 minus. If I plug in 0, 0, 0, tangent inverse of 0 is 0. So I'm going to end up with just minus 0. So if I evaluate this, what will I get?
Pi? Negative pi?
Yes, I'll get negative pi. And that will be the value of that function. I mean, of that integral, not the function. Any questions? Okay, so we've got two more examples in this section, so we will finish those on Tuesday. Um, and basically, we've got, I think, three more sections after this to finish up. So we should be wrapping up more likely during the week before exams happen. Okay, should be wrapping up with all the materials for the course. Um, I don't. Let me look real quick. Yes, I do have a quiz 17, which is going to be focusing on triple integrals and substitution. That is going to be due on Tuesday of next week. So that quiz should be open and ready for you and everything. Okay. I'll be working on over the weekend trying getting your the two quizzes that you just submitted graded and get those that work back to you. Okay. Are there any questions? All right. Well, that is it for today. You guys have a great rest of the day. You have a great weekend, and I'll see you on Tuesday.
You are currently the only person in this conference.